So what is this? What is anticipation exactly, and how does it work? It sounds like the antecedent behavior, and was it? I forget the third term. Um, seems to break down a little.
Consequence.
Yeah, consequence. Yeah, it seems to break down a little bit when neither of neither of the predicates are really even are required.
It's not that it's broken down. It's more general than we'd originally specified. It doesn't have to have an operation as part of the antecedent. It can just be an event will predict another event.
Okay.
Yeah. So it doesn't have to be a condition, an operation predicts an event. It can just be an event predicts another event. So that's kind of the most general form, because the output of any operation is an event. So it kind of covers the behavior case as well as the more general case.
Okay. Can we see how how this flows through the architecture?
Yeah, sure. And is it okay? It's on your screen, all right? Is it? Can you see it? Okay.
Yeah, I can. Yeah.
Okay. So it's basically yeah. Well, I'll tell you as it is now, and then we'll fix the problem with it in a minute after we had a discussion about it. So you were right earlier on, by the way, Jared, when you said that operations are executed as a result of local inference, which is correct. So when a task arrives in a concept, it goes into the local inference process, and then it's revised if appropriate, and then the decision rule is applied, and if the desired value exceeds a certain threshold, then it will be executed. At which point the concept would send the operator execution message along this path up to the operator executor, where the actual operation itself is carried out. Now, because an operation has a consequence or an anticipated event, that goes with the operation because it knows it's going to generate that, ideally. That's its expected behavior. So that goes with the operation request. And when it arrives at the operator executor, it sends that anticipated event message to the anticipated event actor. And it awaits for that actual event to occur as an input task. You following me so far?
Yes.
Okay.
Okay, and I guess I was like, so this is not actually correct though, because
It's
other
half correct.
yeah, it's half of the puzzle, right?
Yeah. So for now, the easiest way to think about it is if the event that's being anticipated isn't the result of an operation, so it's just think of it as a null operation for now. So the antecedent has a null operation, so it's the same except it doesn't actually do anything when it arrives at the operator executor. So it does it can follow the same path. We may want to change that, but for argument's sake, for now, it can still be executed exactly the same way. So there's an operator request gets sent to the operator executor. In this particular case, it's a null operator, so it just passes the anticipated event straight through to the anticipated event actor.
Okay, that's fine. I totally get that part of it. Like the operator executor and the anticipated event seems pretty clear. What isn't clear to me is, I guess, the decision-making process on sending the operator execution message. For example, I'm not so super clear on the desire or its threshold, and if in the case of a null operator, how is that impacted or changed in any way?
Yeah, because the decision operator only applies to operations, so you're going to actually execute a goal. Well, it doesn't have to be an operation, but it does have to be a goal. So yeah, it applies to goals. Well, I guess it's the same thing. So I mean, Patrick, do you want to explain about the decision rule?
Mm-hmm. As Donny said, the decision rule takes a core, and the next thing is when is this rule applied? It's applied when a task is processed. So if a task is processed, which means it's taken out from the buffer, or for example, in 170, we just had a global buffer, and all input tasks and the ref tasks went into this buffer. And processing an event in this version just meant taking an element out of the buffer and then seeing if it's a gore. If it's a gore, then process gore is called. If it's a judgment, process judgment is called. And in case that process judgment is called, the decision rule is applied. And this one does the following. The belief table is checked for the best answer for the gore. And based on this belief, which is projected to the gore, the satisfaction value is calculated, and the more satisfied the gore is, the more the gore gets reduced in its priority value. And the next thing which happens, the gore enters the the desire table, and it can be that there is already a element it can revise with. Then the decision rule stops and derives the ref task, and because this derived task will itself go into the derived task buffer and will be selected with process gore, the same applies. We select the revised gore from the buffer, see that it is a gore.
Sorry,
process gore.
Just to clarify before we can continue, the decision rule, that's part of local inference and isn't a rule in the DSL, right?
Right.
Okay, cool.
So it's really only called when a input or the ref task is selected for processing from this global buffer in 170. In our version we might refine this, but in 170 all the ref and all the input tasks ended in the same buffer. Okay, and so the things it does, to give a big picture, it tries to revise with the best core, which is already in, and if this revision works, then the decision rule is finished, and because it will then anyway be called for the revised core. And what if a revision is not possible? Then it gets interesting. Then it depends on how high the desire value of the core is. If it's above a certain threshold, and if it's an operation, then it gets executed. This was a bit confusing.
Yeah, I'm still trying to wrap my head around it a little bit. I think I get the broad strokes. I guess I need to like look up the decision rule and look around at the logic that surrounds it, because
I think
Yeah,
it's better I try again because this was really confusing.
Please do if you want to. I'd love.
It just needs a different way of explanation.
So we've got a task coming in that's a goal. Then something decision rule, something operator execution message.
Red a gore comes in. Okay, I think I have a better way of explaining it. Imagine what would happen if we would just execute all the gores if they represent operations. The thing is, the system would immediately, if it derives something out of it's not considering or evidence, it might apply wrong decisions. Or, for example, if it already knows that it should not jump down the skyscraper, just deriving this score would let do it. This would obviously be not a good idea if each derived operation core would directly cause an execution. So the system somehow needs to summarize desired value. And how can it, and the way it does this is by its belief, by its desire table. And so if a new gore gets processed, instead of directly executing it, it is checked, the desire table is checked for a revision partner.
So the desire table is would be within the concept actor's memory structure, but it's not currently in the diagram. Am I understanding that?
right. It is in the diagram. It's called the goal table, to be honest, down here, because it's actually goals as opposed to, so one's beliefs, one's goals. So they're either truth and desire or beliefs and goals. But beliefs and desire, that's mixing your metaphors. If I think that's the way to describe that.
Yeah, I like goals. Yeah.
Right. And so we have one big part of the decision rule, namely to summarize desired value. So when a new goal comes in, its first priority is to check whether it can summarize this new goal desire with an existing one. So this has the following effect. If there's already evidence for the system that it should not jump down the skyscraper, even if somehow there will be a gore event which says jump down, it won't do it because it will revise with the previous belief, previous desire in the desire table, and dependent on the result of the revision, the decision rule will judge again. But the point is, summary of desired value is first priority. So it's the first thing which happens in the decision rule to check if it can use the new gore to summarize desired value. And then if the revision has happened, we end up with a new derived gore, which is the revised gore. And this one again gets into the decision rule, probably if it's selected from the buffer. And then the same thing happens. It checks the desire table, whether it can revise. If there is no further candidate to revise this revised gore with.
But to be selected from the buffer, it has to go back out as an operator execute a message and then come back through into the concept again, right? the OpenNARS 2 architecture.
This I think we can this time make better. In 1.7.0 it really went into the global task buffer, and I think it's better if it's just happening in the concept. Namely, if the revision happens, it should not go through the derivation buffer. It should immediately revise and add it to the desired table.
Okay.
Yeah, I'd assume that is what happened actually. 'Cause that is how I put the design together. Okay, I didn't know it was different in 1.7.0. Okay.
Right. And but the decision rule itself is the same. It's
Yeah.
just at first trying to summarize with existing desires, and if it's not able to summarize with existing desire, then it needs to judge whether it should execute it or not. Namely, if its desire value when projected to the current time exceeds a certain threshold, then the execution happens. This is basically everything.
Yeah, that's a lot. That's a lot clearer. Thank you so much.
It's indeed clearer. So it's really only those two things. First thing, try to summarize the desired value. If it's able to summarize, we stop, because then we end up with a derived task anyway, which will be processed by its own. And if it's not able to summarize, to revise, then we check its desired value in respect to the current moment, and if this one exceeds a threshold, we execute. That's the entire story.
Okay. Roman, do you have any other questions or?
I don't have questions, and I feel that I don't understand anything here, but it's okay. I will watch this video tomorrow. Maybe it will help. I don't know. I don't understand what is going on there. So sorry. It's only my problem.
Yeah, it's so basically as far as I understand it, we have those null8 operators.
What? Null?
The null8 layer, they have basically external calls, like API calls into whatever the system is capable of doing, which is outside of the reasoning system entirely. And when it executes one of those operators, NARS is anticipating that this is going to have some kind of effect on the external world, which will be reflected in a new task, input task, that'll give it some information on how the operator behaved. So say for example, you had an operator that was like eval, and NARS decided to call the operator eval with 2 + 2, then it would anticipate a return value of 4, and then it will wait for that to happen. And then once that eval operator has executed, the 4 input task would come in, and it would, if it happens within a timely period, then it gets positive reinforcement. Otherwise, the anticipator gives negative reinforcement to that anticipated event. That, I don't know if that made any clearer or not.
No.
There's a couple of points in there just to confuse you even further. There's 2 types of operations in a way. There's those that the system generates its own response for. So the example that you use, like eval, that would actually probably not require an external input task to be generated, because it could generate its own response to that. So eval 2 + 2, the operator itself would generate the result of that. It would be 4. So if you look at the operator executor actor on the screen here, there is this this message, which is input task message, which goes to anticipated event. So some operators actually generate their own response.
They can be synchronous and asynchronous at the same time. That was my understanding.
I'm not sure that's quite the right description. I mean, some operators will affect the external world. So, for example, if it will move its arm, and therefore that will be something external to the system, and it might perceive that through either its eyes or through a sense of touch or whatever, and that would come in as a perception input. But other operators, like eval as an example, they don't physically change the external world. So you generate the input they would generate directly. So in this case, you have to create the input task for them. So they're kind of introspective in a way, and not in the same way as NAL9 is, but they actually generate their own input. Do you understand the difference between those two? Or I've not explained it well enough yet.
Sorry, I didn't listen. Sorry.
No, that's okay. I'm just saying that there's a couple of different types of operators. The example that Jared used was, imagine you've got an operator that says eval 2 plus 2. So evaluate 2 plus 2. So the answer is going to be 4. But the operator itself can generate the response to that particular operation request. It doesn't affect the external environment. So it actually feeds its own input task back into anticipated events, i.e. the 4 arrives as an event. But other types of operations do affect the external environment. And for those, you create an anticipated event message, and then you wait for the perception system to receive that particular message to confirm it or deny it, depending on whether or not it arrives.
Right, but I think they're still. I think they should be in the implementation. They're exactly the same thing. Like, for example, if you have an operator, say you have an operator that has a return code like immediately, so it would either return 0 or 1 depending on whether it successfully created whatever it was doing on the external world. Then you would have immediately that input task message being generated from that.
Yeah, absolutely.
But at the same time, at least from what I remember of the book, like you could also have that same operator also generating an anticipated event. It doesn't so it can be either one or the other, or it can be both. Yeah.
No, absolutely. It's kind of the events they generate are kind of like proprioception. So it's the system detecting things it's doing to itself, but it can also simultaneously create a change in the external environment as well. So you can imagine moving an arm can change the external environment, but at the same time it can feed back information about the degree of angle that the arm changed.
Yeah, exactly. Yeah.
Right. Okay. Yeah. No. And both of those message types are in the system, and that's why there's an input task message and an anticipated event message. So both of those things can be captured.
Yeah. Okay, that's cool. That's it. I'm sure we've probably completely confused Roman right now.
I can ask questions if you have time. Can I?
Yeah.
Okay, so from the very beginning of all the things, let's start from anticipated event, I mean actor. So as I understand, all tasks will go through this actor, yes? Is it so or not?
All input tasks.
All input tasks will go through this. Okay, and if we are speaking about goals, okay, another way. So this all this process, I mean, operator executor and anticipated event, does it related only to goals?
No, events basically. That's why it's the anticipated event. So in any event.
Event.
Yeah.
Okay.
So something that has the time attached.
Okay. So it may
they,
be judgment, maybe goal, maybe question, or not.
Yeah, it can be. It can be. Well, it's basically anything that's not an eternal event. Sorry, that's not an eternal statement can be an event. So long as it's got a time attached to it, then it becomes an event essentially.
Okay. Can you make an example of I don't know, question that will go through this loop? I mean, anticipated event, task dispatcher concept, then awaited execution message, awaited executor, and again anticipated event. Because I don't understand what can be an example of tasks that will go through all this.
Okay. The one I sent one to Jared earlier, which was, in fact, we can keep. Oh, let's keep everything. So we include operators, conditions, etc. So you've got the full picture. So imagine you've got a statement that says switch 1 is on, and you activate switch 1. It predicts that switch 1 will be off. Okay, that's the statement. So switch 1 is on and activate switch 1. Those two things combined as a compound term imply or predict that switch 1 will be off. Okay.
Okay.
Right. So imagine that's the statement, and that's sitting in a concept somewhere. And now we get a goal that we want to make switch 1 off as a goal.
So it is another event, yes, the new event.
Well, it's a goal. This is a goal as opposed to an event. So you need. I'm kind of setting the scene at the moment. So you've got a statement that's a prediction in time, and you've got a goal that we want switch 1 to be off. Now you have an event come into the system that says switch 1 is on, right? So you've got switch 1 is on as a condition. You've got an operation in the system that lets you activate.
Sorry, Tony.
Switch
one moment. Patrick, can you mute microphone, please? Or I don't know who is typing so much.
Yeah, it's Patrick.
Oh. Okay.
Thank you.
Could we also write down these statements or copy and paste them on the screen or something? Because
yeah. Sorry, let me.
I'm just getting I can't hold all this in my brain.
Okay, let me bring this back, and I can work. I can type in here somewhere. I'm sure I can. What? Oh, let's see. Where can I do that? Anywhere? Let's try that. Does it let me type? Oh, I can maybe type here. So we have a statement, something like, oh yes, can you read that?
Yes.
Okay.
It's a little make it a little bit bigger.
Okay, let me move over here. Right. So we've got switch 1 is on, and the other bit of that is activate switch 1. I could just type. And this implies or predicts that switch 1 will be off. Okay?
Okay.
Almost.
Okay.
Almost there. So that's in the system as a statement. And then we set the goal. We have a goal that we want We want switch. Where are we? We want switch to be off,
Mhm.
and that's a goal, right? And we enter that into the system. Oh, bugger. I want to complete that. Yeah, I can. Right. So now an event occurs, and this event says switch 1 is on now. Oops. Yeah.
Okay.
So that now goes into the system, and it goes into the concepts, and assuming the relevant statements are selected, it tries to satisfy this goal, and through the inference mechanism, it recognizes that if switch 1 is on and we activate switch, then switch 1 can be off. So to satisfy this switch 1 off goal, that will happen in the local inference when it actually tries to activate the actually this is quite hard to do this in a really simple way. The switch 1 off goal will create a derived goal, which will be the previous statement as a goal. So essentially that first statement, which is the compound term switch 1 on, activate switch 1, implies switch 1 off, that will itself become a goal. Okay.
Okay.
Then that exactly. So then that will become the sub goal of that will become switch 1 on, activate switch 1, blah 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 blah, and then a sub goal of that will become activate switch 1. At which point we can then actually apply a decision rule to that operation. I'm trying. I don't know if there's a simpler way of doing this with operations.
Yeah, I'm following it so far. So.
Oh, okay. So within the concept, there's now a goal that says I want to activate switch 1. And when that goal is activated, so something will come in through the derived task route, because that's where the goal was created, right? It's a derived goal, it comes in through task dispatcher, it goes into a concept, and then the concepts where activate switch is stored will then go into the local revision, the local inference process, and we'll check to see whether or not it can summarize the desired values for activate switch or revise them. And if the desired value is high enough, it can then call the decision rule on that particular operation, which is activate switch 1. That was all the stuff that Patrick went through. So when that decision rule says yes, we can activate that operation, it basically sends a message along the operator execution message to the operator executor, which in this particular case says activate switch 1 implies switch 1 off. It carries out the function of activate switch 1 on and sends the anticipated event, which is switch 1 off, to anticipated event. So the act of executing switch 1 should generate a perception that switch 1 goes off, because that's what it does. It's a switch and it's turned the light off. And when that happens, it should generate an event. And when that event arrives in anticipated event, it's matched against the anticipated event of switch 1 off, and if they're the same, then it's confirmation and it's fine, and it will wait a short period of time to test that. It's possible that it doesn't. Yeah, go on.
Is the time that it waits generated by the is that defined in the anticipated event message, or is that defined by? Okay.
It's a system parameter. It's a scale of the duration window or the duration parameter. I think at the moment it's set at 2 times duration.
So what about like longer term goals? Like for example, say like if I don't know, if I push a door, it's and I have to wait like, or I know, like say I push a button on an elevator, and I have to wait another like 3 minutes or something before the elevator has arrived.
Yeah, when there's events that span longer periods of time, then they have to be encoded slightly differently. So you end up with a start event and an end event.
Ah, I see.
Yeah, so you can't just treat them as a single event because events do have durations typically, but the durations aren't specified. But when they're not specified, there's an assumption that they're relatively short. So yeah, we're talking about a duration type time period or slightly longer. If they get longer than that, then you need to specify them as a start and end point.
Okay. And
Yeah, so just to add to that,
Oh.
that's kind of where the intervals come in.
I see.
Remember, we've got the interval notation that can separate events. And again, that works up to a certain size, but once you get above a certain threshold, again, it doesn't make sense to use that. You have to start moving into more complex representations of time at that point.
I see.
Because I mean, yeah, 3 minutes is kind of probably too many, because in terms of cycles, I mean that's hundreds of thousands of cycles. You know, it's kind of past the point where an event actually an interval makes sense.
Right.
You probably need to actually either you literally encode it in a system clock or use some form of subjective time to measure it, but it wouldn't be very precise.
Okay. Okay. So what does the table of events in the anticipated event actor look like? Is it? It's not a bag or anything, right? It's just some ordered list of some sort, I assume.
Yeah, that's a good question actually. I haven't specified that in any detail. I mean, it really all it has to do is look up the content type. So it could just be a map. I mean, I don't think it needs to be any more than that. It's just a map that's keyed on term.
Okay.
So every time a term input arrive, but I haven't thought about that massively.
Maybe just set. Why map? Maybe just set.
Yeah, it could be. Actually, no, no, it can't be a set on content because you can have multiple terms with the same. Sorry, you could have multiple events with the same content but different times.
Okay, but in terms of closure, it can be set. It doesn't matter. So you can just have this input event that will have this time, and you will check if there is an anticipated event with the same time and statement. It's okay.
Actually, thinking about it a little bit more, it probably actually needs to be a scrolling time window because they only last for so long. So I think that the way to do it is there's kind of a fixed array size where each slot represents a time, and then there's a list of entries within each slot, so that every cycle the top slot would disappear. And if the event hadn't arrived by then, you would then send out a negative confirmation message. Yeah, and then you sort of scroll them all up one to the next time window, and then you'd put a new one on the bottom. So it's kind of maybe it's kind of a fixed length queue where every entry represents a time in the window that you're looking at. I probably don't explain that very well, but
no, I think that
because
makes, yeah.
Okay, yeah, it's because they're all relevant. The events are all have to arrive within say 2 times duration. The window can't be any bigger than that, and if there's one slot for each cycle within that window, where each slot is a list of possible events, then you can just literally look through. You still have to search the entire list because it could arrive slightly out of sequence. That's the only issue with that. But we're not. It's not. I don't think it's going to be massive, but we can figure out the best way of representing this. But that's kind of the general principle involved there, is just finding, matching an input to an existing anticipated event, but recognizing when an anticipated event's timed out.
Okay, may I ask questions?
Yeah, far away.
Okay, looks like I understand something at this moment. I feel myself better. The question is, so as I understand, we from the very beginning we have. Oh no, can you undo this change, Tony?
Oh, sorry. Did you need that?
Yes.
Oh no, I don't know. Let me try. No, I can't. Sorry. I'm sorry.
Okay. Okay, no problem. So it is even better. So we have some knowledges in our concepts. So we have some statement, and then we receive some event with goal.
Yeah.
And then this goal will go to general inference cycle with that knowledge, and will generate new goals.
Yep.
And some of these goals will be sent to operator executor if it will. I don't remember. Okay, some of these goals will be sent to operator executor, and it will. And then operator executor will create some anticipated event, for instance, and we will wait for a new event that will confirm or reject this anticipated event. If I speak correctly, I don't know. Is it so?
Yeah, let's keep going. Yeah.
Okay, so what if we create this anticipated event, but the goals that will confirm this event, I mean, the judgment or something else that will confirm this event was received before this anticipated event? Do you understand me? Not.
Just explain the last bit again.
Okay, so imagine that we have some new anticipated event message. So we wait for some event, yes?
Yeah.
But this event occurs occurred, I don't know, 2 seconds before anticipated event.
Right. So it occurred before we posted the anticipated event message.
Yeah.
Yes. What will be the consequences of this?
Okay. Well, it can't be as a result of the operation that you've executed, because that. I mean, you mean if it was the same operation but previously?
Well,
So
I
say
mean,
you previously
there's
you
the
previously
case where there
executed
is
this.
a null operator where no operator gets fired at all. So it sounds like that the situation can actually happen.
Okay, okay. We have this example with switch off, switch on.
Yeah.
Imagine that we have anticipated event message that will says us that you have to wait for some event that will say to you that switch is off now. But
Right.
someone I don't know, out of our system already put that switch off before.
Oh, okay. I see what you mean. Right. Well, in that case, that's going to arrive. If that's going to arrive before you've actually executed the operation, or even executed the goal to do that. So in this case, the switch off will be an event that ends up in a concept. So that goal, in fact, will be true already because switch off has already occurred. So therefore, it won't need to execute the operation to activate the switch because that it's already achieved its goal of switch one off. Yeah.
But imagine the situation when we will send operator execution message and new task message with these two events simultaneously at the same time. It can be
Okay. Yeah. I mean that's possible. I mean the worst that can happen is you'll draw a wrong conclusion. So what will happen is you'll get if it's already off, and you've sent an anticipated event, and you get the event, or the event's already happened. Either the event that's already happened will satisfy the anticipated event, or it will arrive at a point where it misses the window where the anticipated event can be satisfied. In which case, it's actually correct for it to fail because the operation itself didn't actually activate the switch that caused the light to go off. Something else caused it to go off. Yeah.
Yes, but as I understand in this case, if we wait for this new event that will confirm the anticipated event.
But that's fine because that's the reality of what's going on. Even if you didn't create it, I mean, it's kind of one of those things that you believe you do something, even though actually someone else was doing it without you realizing it. You would still believe you did it.
Yeah,
Okay.
Yeah, exactly. So the system will create a belief. It thinks it did it, and therefore it will believe it because it's got reinforcement to that effect. I mean, over time, it will realize if that doesn't continue indefinitely, that in fact it's made a mistake, and that belief will get revised. But I think that's quite a normal thing. You think certain things causing something, and in fact, it's only after more information and trying things in a different way that you realize actually you were wrong about that. That wasn't what was causing it. So I don't think that's a problem. I think that's quite a normal way of functioning.
No, I don't think that this is a problem. I just try to understand all these things, and this is like example that
Okay, right.
can describe something.
Yeah.
So now, like, I feel that I understand what is what these actors actually will do. So I think I don't have any questions for now, but it is what I don't understand now, how the goal will be chosen for.
Yeah, in the local revision piece.
Yes.
Yeah, I think we need to have a detailed session on that because there's quite a bit going on in there. I mean, conceptually it's very straightforward, but there's quite a bit of detail that kind of makes it sound complicated.
And another question that I had is I remember that we have some flow of revision for judgments, yes, for beliefs.
Yeah.
But what is the flow for this revision for goals? Is it the same, or maybe
it's similar? The flow is identical. Just the processing within local inference is slightly different, because it has this summarized feature to check that. It basically wants to make it was kind of what Patrick was talking about earlier about oh, you there, Patrick?
The summary thing
sorry,
is
I'm
also.
gonna just have to just excuse myself for a couple of minutes. I'll be back in a second. You carry on without me.
The revision is basically the same for desire values and beliefs. For desires and beliefs. So the desire table is for summarizing desire, and the belief table is for summarizing truth. And revision happens exactly the same way. The only difference between goals and judgments is that that for goals you have additionally this decision-making role, which you don't have for beliefs. This is the only big difference.
Okay, I
And
see.
and from control perspective, there's a little difference because in inference, the second premise is always a belief,
Mm-hmm.
so can't be a desire. So,
Okay, that was my question. Okay, because we use this beliefs table for general inference, and we choose the second premise for inference, but we don't use goals for or desires for this. Is it correct? Yes. Okay.
correct. Right.
So the only thing that we use desires for is this revision and then decisions. Yes, is it correct? Okay.
Correct.
Now it is more clear for me. Okay, it's fine. And this operator executor, it can create anticipated event and input task. Input task is just another task for. Okay. The difference between anticipated event and input task is that we will not wait for this input task. We will just put it to task dispatcher. Is it so?
Yeah.
Okay.
Yeah. Right.
Mhm. Maybe it's all. I think I understand this now.
Yeah, it's much clearer to me as well.
And the anticipation is also clear, what it does, and
Yes, we wait for some event. If if we have confirmation, we create new task that will confirm this event. If we don't have new event with content that we need, we create a negation for this.
right. But the confirmation thing doesn't need to be done in the anticipation, but because there is, if an input event enters, it will anyway be processed by temporal induction.
I see.
So the anticipation part, if the event comes in, it can just
Yes,
have
I
to
got
do
it.
nothing in this case.
I got it. Okay,
If it is
it's clear.
confirmed.
I'm back, guys. I did hear the discussion. I was just on the end of a wireless mic, but I couldn't speak back. Right.
Huh? And there's a little detail which is important.
Leaving the best till last, are you?
Observable events.
Not all derived tasks which are events can create anticipations. Only these which correspond to observable concepts. And now the only thing which remains what is an observable concept, and this is whenever an input task is added to a concept, it automatically marks the concept observable, because if it was an input task, then it was observed from external. So this is the missing ingredient that not all tasks and not all event tasks can create anticipations, but only those who correspond to to observable concepts.
Okay, I
Does it-
see.
and the reason
Sorry.
the reason for this is this: if the system would derive a own event, a compound event, which it created by own inference, and if this compound event corresponds to if this compound event is not an observable event, it would mean that the system creates a disappointment, and this would mean that the system believes everything to be false just because it is not observable, and this is something which we can't accept. This is why anticipations are only allowed for observable concepts. Imagine, for example, you know that the ISS station is somewhere in space and flying around Earth. Although you don't see it currently, you won't say, no, it's not happening just because you don't see it. And this is why it's important to only let anticipations happen for observable concepts.
Okay, I see. Is there a way for concept to become not observable after it was observable?
No.
No.
The only thing which could happen is that it gets forgotten and recreated.
I see.
Yeah,
And
I mean, it could be recreated in the future as an unobservable concept, but yeah, but that's a different concept at that point.
and it's in this case then it could mean that sometimes it's a bit too restrictive, but it's better to be too restrictive here than the opposite.
Okay, I
Yeah, I
see.
agree.
Cool.
Alright.
It's clear now. Thank you
Yeah,
very much.
so I mean, so basically, what that's saying is that you should only anticipate percepts type events because they're the only ones the system has been able to perceive in the past. It shouldn't necessarily, it shouldn't anticipate derived tasks directly because it hasn't perceived those as percepts.
Yes, I saw this in
depends.
paper.
Right, it depends. If the derived concept, the derived task corresponds to observable concept, then it's fine to create an anticipation.
Yes, as long as it has been a percept that it's perceived some point in the past. Yes.
Right.
Yeah. Right. Yeah, I suppose we should talk about purely derived, never been perceived versus, just derived from input, which could be observable. Yeah. I suppose, well, we should probably just call them unobservable tasks, really, because that is what they are, isn't it? Unobservable or unobservable concepts.
I agree.
So one more question. In that example that you showed me. Okay, no, I don't have any questions. It's clear. Sorry.
Okay, so there is an outstanding issue now that Patrick very kindly identified earlier, which was that anticipation is more general than we'd specified in the implementation paper. Because in the paper we'd specified anticipation as a consequent of operations, but in fact it doesn't have to be an operation. It can also just be an event that predicts another event. So there's a question on the design at this point. This is why I was sort of saying about this null operation for now as a placeholder. I mean, that is a quick and dirty solution to the problem. I'm not I'm not 100% happy with that, but I'm not sure what a better solution is right now. If anyone's got any ideas.
No, you mean that anticipation is a dirty solution?
No. The fact that at the moment, an anticipated event is assumed to go via the operator executor, but it doesn't have to be an operator. It could just be an event. So we
in
could,
the actor model.
yeah. So we could keep this and then just pass a null operator as part of that message, and it would work fine. But there is a degree of redundancy in there then. But that redundancy is maybe less than putting some processing inside the concept to determine whether or not the message goes to the operator executor or whether it goes directly to the anticipated event actor.
I see what you mean. I think in the long run, anticipation should be an operator core anyway.
Okay.
So in the long run, it will be anyway an operation. It's just in 1.7.0, I didn't want to add introspective operations, and so I also didn't want to introduce an anticipation operator already.
Okay. All right. So are we okay leaving it as it is then in terms of structure, and then just if it's a non-event anticipated event, sorry, if it's a non-operation anticipated event, then we just pass a null operator as part of the message, and if it's an operation one, we just pass the operation. Okay, well, that seems the easiest way. Any objections from Jared or Roman on that?
No.
Nope.
Okay, I mean that's certainly the simplest, and it means virtually, well, it means no change really at all. Okay, great.
Cool. So thank you very much for this explanation.
Yeah,
But now
thanks so much.
I need. I
You're
have to
welcome.
sleep.
I'm sure we'll be going over it again.
Okay, I think I will ask some questions tomorrow, but for now
No
it's
problem.
fine.
Yeah, it's late for you guys now, isn't it? Yeah, you're right. You're now actually. How far ahead are you, Roman? What's time where you are?
1 hour past. 1 hour, okay.
Well, you 1 hour past Jared.
I'm in Kiev. It's Eastern European time, UTC plus 2. So
Yeah. So it's
Nearly 1
half past
a.m.
midnight your time. Yeah.
yeah.
Right. All right, guys. Well, if there's nothing else, let you get some sleep.
Good night.
Thank you very
night.
much. Bye.
Thanks a lot. Good night.